Hello everyone, my name is Sophia Arvin Khan and I am going to talk about electron energy loss spectroscopy. So we all know about transmission electron microscopy as it is largely used for material characterization and it provides structural information with excellent spatial resolution. Now this structural data can be supplemented by chemical information from the same specimen region obtained using analytical techniques such as EDS and EELS. And as a broad range of inelastic interactions occurs when electron beam strikes a specimen surface ranging from phonon interaction to ionization process, Eels offers unique possibilities for advanced material analysis. These are the contents I would talk about. First, what is Eels and why do we need this? The principle, plasmon, the spectrum, the spectrometer, spectrum resolution, of course its applications, comparison between Eels and EDX, and lastly the limitations of this technique. Let's look into the principle of Eels. When an electron beam strikes the sample, we can observe a number of processes occurring, like secondary electrons, backscattered electrons, characteristic X-rays, Auger electrons, elastically scattered electrons, inelastically scattered electrons. And by using these different types of phenomena, one can characterize a sample. Eels uses inelastically scattered electrons for characterizing a material. Now, why we need this technique? So actually Eels provides a broad range of applications like local thickness or mass thickness, valence electron density, dielectric functions, elemental analysis, bonding informations, valency or magnetic properties, and of course oxidation state. So in Eels, when we irradiate a sample by an electron beam of known kinetic energy, it triggers many interactions along with inelastic interactions. Due to these inelastic interactions, some amount of energy gets lost during the process, and we can actually calculate this amount of lost energy. Using magnetic prism and detector, we can collect this electron and get a plot which tells us about the number of electrons and their corresponding energy losses. This amount of information tells us about chemical nature and electronic state of a particular material. Now here I have presented the instrument of Eels, how it looks. So Eels is basically attached with the tame instrument, and this is the schematic diagram of the instrument. As I previously mentioned that inelastic interaction triggers different processes to occur which leads to the energy loss. So these are the internal processes due to which the energy loss is happening. It's the plasmon excitation, phonon excitation, inter or intraband transition, inert shell ionization, and negative ion resonance. So I have talked about this plasmon excitation on my next slides in detail. So what is a phonon excitation? It means lattice vibration. So lattice vibration is occurring and which leads to heating up the material, and the energy losses is very low in this process, like it's less than 0.1 electron volt. The scattering angle is quite large for this process, which is around 5 to 15 millirad, and due to this large scattering angle it gives a diffused background. So as we can see, the energy loss is very small, less than 0.1 electron volt, and generally a Eels spectrometer has a resolution of 1 electron volt. So Eels is not a very good technique to detect this kind of excitation or this kind of process. Now next is the inter or intraband transition. So we can also have this kind of transition where due to the excitation of electrons there is a transition occurs between different orbital or between two different shell, or even it can happen between two different atoms. Inner shell ionization, we can allow atom to get ionized by the release of an electron, which gives the elemental information of the material or the sample we are characterizing. The last one is the negative ion resonance. So it occurs when we introduce some impurities as adsorbed on the sample. So these impurities introduces some molecular orbital. So when incident beam uh, strikes the sample, electron get excited and it can get trapped into this high lying molecular orbital. Because of this, some energy is utilized. So the scattered electron, what we get, this has less energy than the incident energy. So as I previously mentioned about plasmon, which causes some amount of energy loss uh, during the inelastic interaction process. So what is this plasmon? So plasmons are analogous to sound waves since they are longitudinal oscillation of the free electron gas. And we generally consider this kind of phenomena for metals, where we consider that the positive charges are into the sea of free electrons. So in this kind of materials, when electromagnetic radiation or electron beam falls upon, it causes the longitudinal oscillations of the free electrons. These oscillations are damped out in less than a femtosecond and is localized to less than 10 nanometer. Plasmon is one of the most common inelastic scattering in the metals or in a material, and it's a very strong features of Eel spectra, what I'll discuss on my later slides also. It can occur in any material with weakly bound or free electron, but they occur predominantly in metals, particularly metals like aluminium, which have large Fermi surface and therefore a high free electron density. The phenomena oscillation is quantized and the mean free path is around 100 nanometer. The scattered angle for this plasmon is less than 0.1 millirad, and the energy losses happening during this process is around 5 to 25 electron volt. So this is a quite good amount to be analyzed by Eel spectrometer, as I have already mentioned that the Eel spectrometer have a resolution of nearly 1 electron volt. So to analyze a spectra is one of the most important thing to do. Now the Eel spectrum has three prominent regions. First is the zero loss peak. So this is an intense sharp peak and it represents electrons which have not been scattered in the specimen or which have been elastically scattered via interacting with the atomic nuclei. The width of this peak is around 0.2 to 2 electron volt, and the FWHM or full width at half maxima tells us about the resolution of the spectrometer. The next region is low loss or low valence region, which appears at less than 50 electron volt, and it contains plasmon peaks, and it's relatively intense. So this peak gives us the information about bond structure and dielectric property of materials. The third region is the high loss region, which appears at greater than 50 electron volt, and here the electron intensity decreases rapidly. For this, the count scale is considered in logarithmic scale. It represents the inertial excitations, and they forms edges rather than sharp peaks. So the inertial rising rapidly and then falling uh, in a more slow manner with increasing energy loss. The sharp rise occurs at the ionization threshold. Since inertial binding energies depend on the atomic number of the scattering atom, these edges reveal elemental informations of the material. Now, if we just zoom in the edge, it will show fine structures oscillation which are due to the bonding effects, and this is termed as energy loss near edge structure. This gives us the information about the bonding and charging state of elements. Now, at higher energy loss region, we can also observe small intensity oscillation due to the diffraction effects from the atoms surrounding the ionized atom, and this called as energy loss fine structure. There is only one kind of spectrometer commercially available, which is mounted on a stem or stem after viewing screen. This is called the Eels or parallel collection Eels. Actually, Eels is a magnetic prism which acts both as spectrometer and lens. Now we can understand, right? Like, okay, so this is a spectrometer, but why lens? Because the electron suffering the same energy loss but traveling in both on-axis and off-axis directions are brought back to the focus in the dispersion plane of the spectrometer. So actually this magnetic prism are also acting like a lens. That's why it is said that the magnetic prism is actually acts both as the spectrometer and the lens. Now, why we use this kind of magnetic prism? Because it is compact and it is easily it can be connected with TAME or STEM instrument. It offers sufficient energy resolution to distinguish spectra from all the elements in the periodic table. This piece is installed beneath the camera system of a TAME, and electrons are selected by a variable aperture entrance aperture where we can actually change the diameter of the entrance aperture from 1 to 5 millimeter, and the electrons then traveled down this drift tube through the spectrometer and are deflected through an angle of greater than 90 degree by the magnetic field. Now the electrons that have lost energy are deflected farther than those suffering zero loss, and a spectrum is formed in the dispersion plane consisting of a distribution of electron intensity versus energy loss. Now electrons suffering the same energy losses but traveling in both on-axis and off-axis are brought back together in the focus uh, on the dispersion plane of the spectrometer. To minimize the different types of aberration, the faces of the prisms are curved. And again, another important thing is the spectrometer contains asymmetric lenses. So we have to fix both the objective distance and image distance if we want to keep the spectrum focus. There are two types of imaging filter used in Eels. One is the in-column filter, another one is a post-column GIF. The in-column filter placed between the intermediate and projector lenses such that the recording CCD detector only receives electrons that have come through the filter. So all images consist of electron of specific energy. The post-column GIF is added below the tape viewing screen. This is the post-column GIF, which is actually a peels with an energy selecting slits after the magnet and a 2D slow scan CCD detector rather than a 1D PDA or photodiode array. Compared to standard spectrometer, there are many more quadrupoles and hexapoles in the optics of GIF. The slit has two functions. Either it can project an image of the spectrum onto the CCD, or it can compensate the energy dispersion of the magnet and project a magnified image of the specimen onto the CCD. Again, it has some drawbacks. The post-column GIF, of course, have some drawbacks, like it introduces some astigmatism, and the operational difficulties is also quite high for this. Next one is in-column or omega filter. It is placed between the intermediate and projector lenses and consists of a set of magnetic prism arranged in an omega shape which disperses the electron off axis, but in the end brings them back onto the optic axis before entering the final projector lens. Here each of the four prisms is mechanically with curved faces to reduce the aberration. The entrance apertures select an area of a specimen, and the beta, or the collection angle, is governed by the objective aperture. Electron following a particular path through the spectrometer can be selected by the post spectrometer slit, so only electrons of a given energy range are used to form the image. The spectrum appears as a line of varying intensity, then the computer changes it to a traditional spectrum of count versus energy loss. So the monochromator is a very important part of Eels because if the spectrometer is not the limiting factor, then the gun dictates the ultimate energy resolution. And eels require FEG or field emission gun. Basically, a monochromator is an eel system fitted on the FEG source, and the slit refines the already narrow energy spread still further, giving remarkable fine details in the spectra. The commercially available monochromators are usually wind filter which has perpendicular electrostatic and magnetic field which permits the chosen electrons to travel in a straight line down the TEM column. The alternative of these commercial monochromators are the softwares which gives a resolution around 200 millielectron-volt. This plot compares the FWHM of the cold FEG and the commercially available monochromator, and we can easily conclude from here that the commercially available monochromator provides higher resolution to the Eels system. These plots again compares different sources of electron beam, and again we can see that this commercially available monochromator provides higher resolution to the system. So there are of course some drawbacks if we use this kind of monochromators, because in fitting out the tails of the Gaussian energy distribution to reduce the FWHM, we actually reduces the number of electron significantly. So this is a quite important, like quite huge drawback of this kind of monochromators, because we are actually wasting lots of number of electrons for this. Spectrum resolution. So the energy resolution of the spectrometer defined by the FWHM of the focused zero loss peak, and the type of electron sources also determines the resolution, as I have already talked about it. At 100 kilo electron volt, a tungsten source has the worst energy resolution, around 3 electron volt, where a Lanthanum hexaboride is slightly better than that at 1.5 electron volt, and a field emitter can give a 0.7 electron volt, which is quite good resolution, and a cold effigy gives the best value of 0.3 electron volt. All these values will get slightly worse at higher electron volt, and the energy resolution also decreases slightly as the energy loss increases. Operating at higher voltage also degrades the energy resolution. And for to get the best energy resolution, it requires a small projector crossover and a small entrance aperture, giving a collection semi-angle of 10 millirads. Now, different factors can affect the resolution of Eels spectrometer. First one is the specimen. So if we use a too thick specimen, it causes pleural scattering, and it greatly increases the background to ionization edges below 1000 electron volt, making these edges invisible to us. The next one is the spectrometer collection angle. The collection angle beta of the spectrometer is a most important factor. Poor control on this value leads to error in the quantification, and we can calculate this from this formula, which is beta is equals to d by 2h, where d is the distance of diameter of the entrance aperture, and h is the specimen and aperture distance. Larger the collection angle, high will be the intensity, but it gives poor energy resolution. On the other side, smaller collection angle gives a higher signal to noise ratio in the spectrum. The third one is the spatial selection. So in tame diffraction mode, one can select the area of the specimen using either SAD or CBAD. For CBAD, the area we select is a function of the beam size and the beam spreading, which is generally less than 15 nanometer wide. So this is the best for high spatial resolution of Eels. The last one is the electron beam current. The higher beam current can lead to broader peaks and decreases the resolution due to increased interaction of the electrons. Now the application of Eels spectrometer. So I have already mentioned that Eels spectrometer shows various kind of applications. The first one I would like to talk about is the thickness measurement of the sample. It measures the thickness of samples using two different methods. One is the log ratio method, which is based on the measurement of the integrated intensity I naught of a zero loss peak relative to the integral IT of the whole spectrum. And we can get this equation from the Poisson statistics of inelastic scattering. This equation gives us the T by L ratio, where L is the plasmon, and this ratio provides a measure of the relative thickness of different areas of the specimen. Next is the Kramer's sum rule, and this is based on the integral over all the energy loss excluding the zero loss peak, and it can be calculated by running a short computer script by the software. The second application is the electronic properties of semiconductor and insulator. So as the size of the devices shrink towards nanometer, TAME and Eels are used increasingly. It is very much useful to determine the band gap of a semiconductor, and as the band gap energy is related to the intensity of these two equations, so we can easily characterize the type of semiconductor, and also we can calculate the energy of the band gap, right? So for the direct band gap, we can see that the intensity is proportional to E minus Eg to the power half, and for indirect band gap, the intensity is proportional to E minus Eg to the power 3 by 5. So from these two equations, we can actually determine that if it is the band, which kind of band gap it is actually referring. Eels can be also used for the elemental information of biological molecules. So here we can see a sharp zero loss peak, and after that at around 25 electron volt energy loss, a peak is observed due to the plasmon. Now if we expand the spectrum, there we can see L23 age of phosphorus and K age of carbon, nitrogen and oxygen. And this L23 age of phosphorus is due to the excitation of two p electrons, and the K ages of carbon, nitrogen, oxygens are for the excitations of 1s electrons. Now this age will be more clearly visible if we eliminate the background intensity. Now we can also quantify the amount of these individual elements by this equation, where S is the integrated core age intensity for X element, I is the integrated zero or low loss intensity for the same energy window delta, and sigma x is the corresponding partial ionization cross section. We can also calculate the elemental ratios, and from this ratio we can localize high concentration of nucleotides that contain phosphate group. Yields can be also used to determine the oxidation states of different solids. Like in this case, I have mentioned the manganese, and manganese has some stable oxidation states of +2, +3, and +4. This oxidation states of manganese systematically influences the spectra, the yield spectra, like the intensity, the shape, the energy of the peaks. And by observing the peaks, we can actually determine the oxidation state of manganese. The high loss region contains the L2 and L3 peaks of manganese and the K peak of oxygen, and the low loss region contains the M23 peaks of the manganese. Like in this case, if we observe the spectra tents, then we can easily see that the average oxidation state decreases, the intensity of the ratios of L2 and L3 peak increases, and both the peaks tends to shift to a lower energy also. So from this we can easily determine the oxidation states of manganese. Now both EDX and ELS are widely used for the material science, and this is just a comparison between the two techniques. It's not to conclude which technique is better, but just to compare between them. So uh, for the ease of technique, if we consider only the ease of technique, the EELS is simple to use, where EDX is slightly more difficult than EELS. The spatial resolution of EELS is better than EDX. The visibility of EELS is low, where that is for EDX is high, and the peak overlap is very few in the cases, because uh, in EELS we have seen the range, the energy range is not very high, so we don't get that much of peak overlap. The sensitivity of yields is high for light elements, and yields is generally used for light elements and low for heavy elements, where for ETX it is good for high elements. So of course, if we like to characterize any heavy elements, we will choose ETX rather than the yields. Lastly, the limitations of these techniques. Previously, I have only talked about the good things of the yields, like the applications of this and how it improves and how it gives us the chemicals and elementals information of the samples. But of course, again, these techniques have some limitations, like the sample damage can occur due to the high energy electron beams used in yields. The instrumental constraints, high performance yield spectroscopy requires a sophisticated and expensive instrumentation. uh, which also includes the aberration corrections. So, of course, it's a quite high cost instrument also. The complex data interpretation. Interpreting Eel spectra requires expertise and it is often complex. And lastly, the low signal to noise ratio. Obtaining high quality spectra with good signal to noise ratio can be a challenging thing for ELS spectra. So, by this, I would like to end my talk here. Thank you everyone for your patience. Thank you.